let us begin. All right, so up to this point, we had originally started talking about functions, machines, or Mustangs, right? We talked about these special types of relations where we had an input linked to an output in a very specific way. And so we spent a lot of time looking at linear functions and then systems of linear functions, right? And how these systems interacted with each other. And then we talked a lot about matrices, which was another way for us to process systems of linear equations. And today we leave the linear equations behind and begin moving towards our more advanced functions. So we're going to start with our quadratic functions. All right, so well, we've looked at all of these, yes, but now what we're gonna do now is, just like we did a deep dive on linear functions, now we're gonna begin a deep dive on quadratic functions. Okay? All right, so first thing that you need to know, you are going to see these two words used interchangeably. A quadratic equation can also be called a quadratic function. And this is an equation to the second degree. We're going to talk a lot about degree as we continue to move forward. But that means that the variable with the biggest exponent is the second power. So this is to the second. All linear functions are x to the first, or input to the first power. And all quadratic functions are going to be our input to the second power. Okay? Now, we looked at previously parent functions and other types of quadratic functions in our common functions sort of quick overview, okay? But keep in mind, when we talk about a function, we're talking about this input-output machine, right? So let's draw our little input-output machine around here so that we remember what it is that we're doing. So our x is our input, and our f of x is our output. Everybody good with that? You remember this, right? And f of x, and we can interchange that with y, and we will interchange that often. All right, now, let me just give you a quick glance at what this looked like for you previously. Okay, now let me just show you just a couple little quick things. Look, there's the parent function right there. That's the one that I just showed you on the paper that's in front of you. Here's another version of that, and yet another version of that, and yet another version of that. Okay, now what we had done previously was calculate all of these points by plugging in inputs and getting outputs to create these pictures to go from heads to tails. Anthony, stop talking. I've given you so many opportunities. Now stop. We have work to do. All right. So now we're going to look at these from a different perspective, okay? But let's establish what we need to know right off the get-go, okay? So what we're doing with these input values is we're taking them and we're driving them through this machine right here. Now let's rewrite this just a little bit differently, right? So that we can see our y equals, and then we can do our parentheses for our input like this. This is another way that we could look at these two things and see them the same way. Right, so when we take our values and we drop them into this function machine, remember, when I take a -3 and I drop it in here, that means -3 squared, right? Which is -3 times -3, or what is the result of that? 9. Positive 9, right? Okay, if I take a -2 and I dump it in there, I'm going to get a positive 4. If I take a -1, drop it in there, I'm going to get a positive what? How about a 0? 0. Okay. Now what happens if I drop a positive 1 in there? I'm still going to get a positive 1, and then a 2, 4. Positive 4, and then a 3, positive 9. And this is what creates the foundation for our parent quadratic. Okay, so our parent quadratic, we're going to plot some points here. So we're going to start here with a point at our 0, 0. And then we're going to put a point at 1, 1, and then a point at 2, 4, and then a point at 3 and 9. We're also going to have a point at -1, +1, -2, +4, -3, +9. Okay? And again, this is not linear, right? If I take a line and I draw it through my 0, 0 and through this point, I'm not going to hit any other points. If I go here, I'm not going to hit any other points. If I go here, I'm not going to hit my other points. This is not a linear function, and so this has this kind of smooth, curved graph that comes down and just right at that one point and just kind of kisses that x-axis right there at that one exact point. Okay? All right, now, we're going to come back and talk about something in just a second, but let's talk about what this shape is called. So this is a parabola. Okay? Now, the parabola is a symmetrical shape. Okay? So that means that it can be folded on top of each other, and it would line up exactly. And so where our fold line is what we call the axis of symmetry. I'm going to abbreviate this often AOS. You'll see it written like that on your assignments. When I say what is the AOS, I'm asking you for the axis of symmetry. And for all parabolas, that is going to be a vertical line, and it's drawn cutting the parabola into 2 equal halves. All right, it's going to be drawn cutting the parabola into 2 equal halves. So here's what I want you to do. I'm going to use a red color. You can use whatever color you want, okay? But I want you to draw a dashed line, a dashed vertical line where you think the axis of symmetry is. If you're not sure, then just put your finger there. Kind of where do you think the dashed line for the axis of symmetry for this particular parabola would go? Okay, so you're putting in a dashed line where you think it should go. So you should have identified this line right here as your axis of symmetry. Now, I kind of drew my color just a little bit off to the side there just because it's such a dark line. But this is the y-axis, correct? Yeah. Everybody good with that? Yes. All right. However, we are going to refer to our axis of symmetry as a equation, a vertical line equation. So let's just do, and you're going to leave a little bit of space here. Give yourself a little squiggle. All right, and let's remind ourselves a couple things. Number one, horizontal lines, this is linear functions, right, are always written in the form y equals, and vertical lines are always written in the form x equals, okay? So you can see here it says, what is the equation for the line of symmetry for the parabola above? So let's just swoop a little arrow right here. And I want you right here to write what you think the equation for the axis of symmetry line is. Go ahead and write that down right now. What do you think the equation for the axis of symmetry is? If you got it right, you should have put x equals 0. So again, the way you interpret this information is the vertical line that crosses the x-axis at 0. Catch it? I'm going to say it one more time. This is the vertical line that crosses the x-axis at 0. Okay? That's what the axis of symmetry is for the parent function. Okay? Now, I'm going to highlight this right here because you're going to hear me refer to this often. And I'm going to refer to this as the parent function pattern. The parent function pattern. Okay? So here's the way the parent function pattern works for quadratics. Remember, the math is we're taking an input and we're squaring it to get an output. Put in a 1, get out a 1. Put in a 2, get out a 4. Put in a 3, get out a 9. Put in a 4, get out a 16. Put in a 5, get out a 25. Put in a 6, get out a 36. Yes? Okay. So I will often repeat myself and I will say, I'm talking about the 1, 1, 2, 4, 3, 9 parent pattern for a quadratic function. You move like this. I'm going to do some highlights. You move 1 to the right and 1 up. You move 1, 2 to the right, and you move 1, 2, 3, 4 up. You move 1, 2, 3 to the right, and you go 1, 2, 3, 4, 5, 6, 7, 8, 9 up. Parent pattern. 1, 1, 2, 4, 3, 9. Axis of symmetry means that it's exactly the same on the other side. Left 1, up 1, left 2, up 4, left 3, up 9. Parent pattern. This is how you're going to be graphing your quadratic functions in a particular format that we're going to talk about called vertex form of a quadratic function. So you're going to use your parent pattern 1, 1, 2, 4, 3, 9 to graph these things. Okay? And we'll talk about how that's going to work. Now, let's get some other language established in here. The vertex of the quadratic is the turning point. Okay? It's the turning point of the parabola. And it's where the parabola crosses, watch this is really important. It's where the parabola crosses the axis of symmetry. So the vertex always sits on the axis of symmetry. Did you get that? That's really important. The vertex always sits exactly on the axis of symmetry. Okay? Now, if we were going to label our vertex here above, and we're just going to swoop a little arrow here because it's a little hard to do it on the picture. Our vertex would be 0, 0 for this particular graph. Okay, this is our vertex. That's what it asks us right there. What are the coordinates of the vertex? Okay, now everybody look at me. Okay, we are going to have two things happen here. Our parabolas are either going to open up or they're going to open down. They're never going to open sideways. That's a totally different relation. In fact, it's not even a function, right? Think about the vertical line test. Okay, that's called a hyperbola. It's not going to be a function. But parabolas are always going to be a function because they're always going outward and upward. Okay, so they're always going outward and upward, and they're always going to either open up or open down. So then that's going to give us some specific language to refer to our vertex. Like, for example, if our vertex of a parabola that opens up, we're going to call that a minimum. It's the lowest point on the graph. Get it? Now, for a parabola that opens down, our vertex is going to be called, what do you think? A maximum. That is the highest point on the graph. Remember, height refers to up and down, which is which axis? Y-axis, right? So when we say it's the lowest point on the graph, we say that's the lowest in the range. Oh, remember that? And domain, yeah. Taking the biometrics, right? Before the physical, yeah. All right, we're going to talk all about that stuff. That's what you're going to have to be able to identify. So a minimum is the lowest point in the range, while a maximum is the highest point in the range. Okay, everybody good there? All right, so let's jot that down. So we want to make a note here. If our vertex, it will be a maximum if the parabola opens down. And our vertex will be a minimum if the parabola opens up. Okay. So our vertex will be called a maximum if our parabola opens down, and it'll be called a minimum if our parabola opens up. Everybody good so far? Okay. All right. Now's where it gets a little tricky. You're going to need to watch carefully up on the screen, because this is sort of I'm going to do a little exhibition for you so you can see something that you're going to then have to do on your homework. So you're going to want to pay close attention to what I do up here on the screen. Here we go. Okay, what you see before you up here on the screen is the parent function that we just drew on our notes. You can see it right there, right? 1, 1, 2, 4, 3, 9. Okay? It's a parabola. It's got the left 1 up 1, left 2 up 4, left 3 up 9, like that. Okay? Now, what we're going to begin talking about today is something called a transformed function, right? These are math equations, right? And the way we do math to these things is what changes the picture. We saw that with our linear functions, right? When you change the slope of a line from positive to negative, that line was going like this. Now it goes like this, right? And we do that by multiplying by -1. That's how we change the slope of a line from positive to negative. So let me show you what the generic transformed function looks like. This is what we call vertex form of a quadratic equation. So you'll notice that now I've brought in an A, an H, and a K. All right? Now I want you to notice there's a specific order, follow your PEMDAS, there's a specific order in the way that the math is done, and that makes the difference in the way that the picture turns out. For example, the H. Okay? The H does math to the input before it's squared. See that? Then we square. Then we multiply by A, because it's right out in front of a parentheses. And then the last thing we do is we add and or maybe subtract a K onto the end. So the order in which we do this math is going to change the way this looks. All right, now let me show you how this looks in this particular case. This is our parent function. This is what the transformed parent function looks like. Study that for a second. Think about what I replaced for variables and numbers up there. Okay, let's talk mathematically for a second. Let's take the 2, 4 point. Let's take this 2, 4 point for a second, right? Input of 2, output of 4. Let's take the transformed parent function. If I put a 2 into my function and I take away 0, what am I left with? Okay, so then I square it. 4 times 1 is? Plus 0 is? Okay, so put in a 2, still get out a 4. Does that make sense? Yeah. Right? And it works like, let's take -3. Put in a -3. If I take away nothing from -3, okay, square it. +9. Multiply by 1. Still +9. Add nothing. Still +9. Right? It works, right? Okay, but here's what we're going to start doing. Watch this. We are going to take our generic transformed equation. I'm going to turn it on here now so you can see it in orange. Okay? So now I've got the blue is the parent function. And now I've got in orange, that's the transformed function. And now I've got some controls that I can work with here. Here are my A's, my H's, and my K's. Now remember, these are different numbers I can put into the math equation that is going to affect the visual graph. Like for example, right now currently I'm not subtracting anything from the input, right? But if I subtracted 1 from the input, look what happened to the picture. Or 2, or 3, or 4, or 5, or 6, or 7, or 8. Or what if I added something to the input by making my H value negative? What's happening here? How is it moving? Okay, so it's moving left and right. Now, I want you to notice something, okay? Look at the Y values as I move the graph in the orange. Watch the Y values. Do they change at all? No. Look at the X values. Do they change? Yes. Okay, and they're changing exactly by how much I move. Like watch, if I come over here and I move my graph over here, you can see I went 4 to the right. That's my H value, +4 to the right. And look, everything that's x moved plus 4. Negative 3 plus 4 is 1. Positive 3 plus 4 is 7. 2 plus 4 is 6. See it? Everything shifted 4. Okay, let's pull this back for a second and put it at 0. How about if I change the math that I do by adding and subtracting after I've done all my squaring and multiplying? Watch what happens when I do that.
Ew.
What's happening here? Okay, all right, so it's moving up and down, right? Now, notice the x values of the orange one. Do the x values change at all? But the y values do, right? So I could do some combination of this, and I can shift my graph around however I want, right? Okay, so that's important. So the way I change the math of addition and subtraction is going to change the positioning of the graph. All right, now watch what happens when I change the multiplication on my generic function. Right? Okay, now did the vertex move at all?
No.
So the vertex stayed the same. So it's not sliding around, but it's almost like I'm taking those y values and I'm stretching them up. In fact, look, if I zoom out here to a further distance and I stretch those up, I'm pulling those y values up that axis of symmetry, and so it's stretching them out. But let me just show you the math of it. Watch. I'm just going to come to a simple number like 2. Okay? Let's zoom in again. What was the parent pattern? 1, 1, 2 what? 3. Okay, but now when I put a multiply by 2 in there, after I get my 1, my 2, and my 4, and I square it, now I multiply by 2. Now it's not 1, 1, 2, 4, 3, 9, but now it's 1, 2. Okay, it's hard to see. There's 1, 2, and then look, there's 2, 8, and there's 3, 18. I'm taking that output and I'm multiplying it by 2. And so those y values are going to increase faster, and so it's going to go up a lot quicker. Does that make sense? Okay. All right. Now watch this. When I take that number and I multiply by a fractional value, look what happens. It pushes out. It's almost like I'm putting a ball in the middle of that parabola and compressing it down. And I make that parabola go wider. Okay? I stretch it narrower. I compress it wider. That's going to be really important language for you. Okay? Check this out. Watch when I take it and I make it negative. So now I can make my A value, right? Now I have a maximum and not a minimum. Okay, that should tell you something about the sign of the A value. Will tell you whether you have a maximum or a minimum parabola. Okay? All right, but now watch this. Let me just show you something here. Watch. I'm going to just go to right to -1. So all I'm doing is taking my outputs and multiplying by -1. That's early. Hold on. 110. We got 5 minutes. 110. Oh, no, it's not. It's 105, is it? Oh, crap. Okay, well, I'm going to give you your homework anyway, and I think you can probably figure it out. You're going to be doing A, H, and K's, and you're going to play with it. And you're going to open up a Desmos graph like this, and you're going to monkey around with it and take some screenshots. Okay? All right, let's see what you can do with that. I'll see you tomorrow.